I don't want
Um, so like I said, we're just gonna start topic 4 today. Even though you've got your test tomorrow. You said tomorrow, yeah. So you got. I just don't expect this is not going to be on the test at all. Okay, nothing I teach today is going to be on the test, so you're good. It's just on topic 3. So the first topic in topic 4 is simple harmonic motion, and it's a pretty straightforward concept, but there's a lot of variations to the equations that you're going to see. So it's going to be like equation intense, but it's not that challenging. It's all based on circular motion. All right, and we've already seen circular motion, so you should be comfortable with this material. Okay. I said the joke is not so simple harmonic motion because there's so many equations, but it's not too bad. A system is said to be oscillating if it's moving back and forth in a regular repeating path. An oscillating system is exhibiting simple harmonic motion if the object follows a linear path and its amplitude, velocity, and acceleration can be modeled using a sinusoidal function. Okay, so instead of a wheel where we're going around in a circle, now we've got something moving back and forth or up and down in a straight line path, but its amplitude can still be modeled over time using a sinusoidal function. Okay, so the one that we usually, the type of system that we're going to start with is just a spring mass system. Like if you had a spring, mass on a spring and it's just going up and down or side to side. All right. Right off the bat, we have 2 requirements for simple harmonic motion. First requirement is that the force acting on the object must be directly proportional to the object's displacement. So we know that a spring would fit this criteria because of which law that you already have learned. Yeah, well, what's spring constant law? Hooke's law, yeah. Hooke's law, we already learned that the force is directly proportional to displacement. So a spring is a perfect medium to set up simple harmonic motion. And lastly, the force acting on the object must be directed toward the object's equilibrium point. Meaning that the force is always pulling it back towards equilibrium. It's not pushing it away from equilibrium. Again, if you just keep a spring in mind, it makes sense. So the x-axis here is going to be distance from equilibrium. So from the first rule, or the first requirement, we saw the force has to be directly proportional. What type of graph does that bring into your minds if I say something is directly proportional? Ben? Straight line, great. Now, the second rule is going to tell us whether it's a negative slope or a positive slope. So think about it. If the force has to be always pointing towards equilibrium, if we're on the left side of equilibrium, then is the force going to be positive or negative? Think about it. If we're calling right positive, okay? If I pull the spring this way, what way is the force pulling it? Sue? Yeah, to the right. So when the object is to the left of its equilibrium point, or in the negative, whatever we call negative distance, the force is going to be positive, pushing it back towards its equilibrium point. So we end up with a pretty simple graph. Let's blue. Now this graph doesn't go on forever. What does this point and this point on the x-axis represent? Its maximum displacement. Okay, so that would be the amplitude of its motion. Oh, I guess we should do min and max. Okay, A stands for amplitude. Oh, sorry, I should talk about the footnote here. Right from way back at the top. Talking about it has to follow a linear path. What we're going to see the next time we do part 2 of this note is that some things are approximately a linear path. So for example, we can take a pendulum and we can say that it's approximately the bottom point, as long as we're not pulling it up too far, the lowest point is approximately following a linear path back and forth. So we use something called small angle approximations. It's a grade 12 trig concept. But we'll do that on Monday. Okay, we're not going to worry about that right now. For now, it's just a footnote. Okay, any questions so far? Well, page 1. Good. All right, page 2. I have a simulation to show you here online. Favorites. Way down at the bottom. All right. So the first thing we're going to use to visualize, or to A, visualize simple harmonic motion, but B, derive some of its first equations, is the projection of a peg on a wheel. Okay. So if you think of the peg casting a shadow on the floor, as that peg goes around the wheel, and we trace its left and right amplitude, instead of looking at it from 2 dimensions, we're just looking at it from 1 dimension, or looking at it from overhead. We can see that that peg is actually tracing out a perfectly sinusoidal graph. Okay, and that's just its projection on the floor. And we're going to use that relationship between its left and right amplitude, or up and down amplitude, to derive some of the formulas from circular motion. They fit nicely together. Okay, so it says an easy way to visualize an object undergoing simple harmonic motion is to look at a peg on the side of a spinning wheel. If the peg's amplitude in 1 dimension is plotted over time, the resultant graph will be sinusoidal. In fact, simple harmonic motion can be thought of a projection of circular motion. Okay, so we're just projecting circular motion into one direction, 1 dimension. Say 1 direction. Oh God. Yeah. Okay, so let's start with some of the formulas here. The distance that the peg on the wheel travels in 1 rotation is equal to the circumference of the circle, and the time it takes is 1 period, right? We already saw that, capital T for period. So, very first one here,